Swayam Prabha. Digital India. Educated India.
This is the first lecture of course on engineering mechanics. In this lecture, we will be discussing fundamentals of engineering mechanics. When we study a course, we must have some motivation for studying this. So therefore, let us see some typical examples where engineering mechanics finds application. Now this slide shows that a car moving on the road. If you have to design the car which runs at a particular speed, let us say 140 km per hour on some expressway. Now you have to find out engine power, forces acting on the car body. The forces will come due to wind resistance, rolling resistance and inertia. So all these type of things you have to do, then you must know engineering mechanics. Then if you want to design a CD drive motor and you want to find out the power needed for a CD drive motor, then also engineering mechanics must be applied. Now this is a figure of a turbine. Now a nozzle issues a jet of water with a high velocity which impinges upon the blade of the turbine. The blades deflect the jet of water through an angle. You have to find out the forces exerted by the jet upon the turbine. This problem also can be solved using engineering mechanics. Similarly, if one has to design a robot for doing a task of picking an object from one location and placing it at another location, then how the movement of robot should be planned so that it accomplishes the task without jerks, that is called path planning of the robot. So such type of problems also require knowledge of engineering mechanics. Now, so to deal with these type of situation, we must need to study engineering mechanics. We study engineering mechanics to develop the capacity to predict the effect of force on motion while carrying out the creative design functions of engineering. Now there can be two type of problems. One is the dynamic problem, in which we study the motions. Other is the statics problem, in which the motion is not studied, but only what is the effect, what type of forces are acting on various components. These type of things are studied. We can define mechanics as the physical science which deals with the effect of forces on objects. We shall follow continuum hypothesis while studying mechanics. A hypothetical continuous distribution of matter is called continuum. Now a body actually consists of several particles. Each particle can be subdivided into molecules, atoms and electrons. It is not feasible to solve an engineering problem by treating a body as a conglomeration of such discrete particles. The body is assumed to consist of a continuous distribution of matter. In other words, body is treated as continuum. Now the next figure shows this concept. Here this is the actual material in which there are particles, there may be some wires in between, but the idealized material is considered continuous. There is a continuous distribution of matter here. Therefore, what happens if mass density rho at a point P in a continuum is defined as the ratio of the mass element delta m to the volume element delta v enclosing the point in the limit when delta v tends to 0, then density rho becomes limit delta tends to 0 delta m by delta v, that is dm by dv. Now, here we have taken the assumption that the mass is continuous function of the volume. That is why we could take the limit. Now, if you know we consider the actual material, then in the limit we may end up in a void. So, this is the thing. So, therefore, in solving the day to day problems by engineering mechanics, we usually apply continuum assumption. Now, this course will act as a foundation for fluid mechanics and solid mechanics courses. There we deal with the deformable bodies also. However, in this course we will be studying the behavior of rigid bodies under force. No body is rigid, it is only a concept based on some assumptions. Now, a rigid body is the body which can be considered rigid when the change in distance between any two of its points is negligible for the purpose at end. So, in this suppose this is a body. Now, in this now if we apply the force, then the distance between two particles remains same. Now, therefore, this body can be considered as a rigid body. Now, next, deformable body. A body is considered deformable when the changes in distance between any two of its points cannot be neglected. In this case, that if imagine that this is made of a rubber material, and if there are two particles, if you apply the force, then the distance between these two particles changes. Suppose this particle is here, after the application of the force, these can be here, and therefore, this body is a deformable body. Now, some note on the history of mechanics. Mechanics is one of the oldest science. Now, earliest recorded writings in mechanics are those of Archimedes. It is 287 to 212 BC on the principle of lever and the principle of buoyancy. First investigation of a dynamic problem is credited to Galileo in 1564 to 1642 for his experiments with falling stones. Year in which Galileo died, Newton was born. Newton was born on 1642 and died on 1727. He has provided 3 laws of motion, and for that he is very famous. On his name, a portion of classical mechanics is called Newtonian mechanics. Later on, alternate formulations for mechanics problems were provided by Lagrange, who was born on 1736 and died on 1813, and Hamilton from 1805 to 1865. Their formulations are based on the concept of energy. Okay. So, now classical mechanics fails when a body approaches the speed of a light, or when body size approaches a size comparable with those of atoms. Relativistic and quantum mechanics are used for those situations. In the present course, however, we limit our discussion to classical mechanics. Let us understand some fundamental definitions, because these terms we may be using again and again. Space. What is a space in mechanics? It is a geometric region occupied by bodies whose positions are described by linear and angular measurements relative to coordinate system. So, there will be a space in which bodies are placed, and position of the bodies is described by linear measurement from some coordinate, some origin, and angular measurement. Time, it is a measure of the succession of events and it is a basic quantity in dynamics. Mass, mass is a measure of the inertia of a body, which is its resistance to change of velocity. Force, force is the action of one body on another. For force to apply, there should be presence of another body. A force tends to move the body in the direction of its action. The action of a force is characterized by its magnitude, by the direction of its action, and by its point of applications. So, three things are important, that magnitude of the force, direction of action, and point of application. Particle, we use the term particles again and again in the dynamics. Particle is a body of negligible dimensions. Particles dimension, particle is having a mass, but it is not having dimension. Scalar quantities, these are the quantities characterized by only magnitude, such as mass, temperature, etc. Now, these quantities are invariant under coordinate transformation. If you know some mass is some object is weighing 1 kg in one coordinate system, its mass will be same in the other coordinate system. Similarly, the temperature also, if we rotate the coordinate axis, these quantities do not change. Vector quantities, these are the quantities characterized by magnitude and directions, such as velocity and force. They have, velocity has a direction as well as magnitude, like that force has a direction as well as magnitude. We indicate vector quantities by bold-faced letters or put a sign of arrow on the top of alphabet, like this is a vector. So, like that. Now, vectors will definitely change under the coordinate transformation. So, if a vector has some components in one coordinate system, in another coordinate system its components will be different. Free vector, it is a vector whose action is not confined to or associated with a unique line in space. Only the direction and magnitude of the vector remains fixed. Suppose I make a vector like this, and if I make another vector which is parallel to it and same magnitude, and it can be considered equal, then naturally this vector is a free vector. So, the free vector is having fixed direction and magnitude. However, it can be placed at any point in the space. Sliding vector, it is a vector which may be moved along the lines of action without change of meaning. For example, if we are towing a cart by rope, in this case, whether we apply a force at this point or apply at this point, it is having usually the same effect. So, therefore, it is a case of a sliding vector in which line of action remains fixed. This is the line of action, but the vector can be placed anywhere on that line of action. So, therefore, this is an example of sliding vector. Sliding vector is a vector which may be moved along the line of action without change of meaning. Okay, so this is this thing. Now, what are concurrent forces? Two or more forces are said to be concurrent at a point if their line of action intersect at that point. So, this figure shows that three forces meeting at a point. This shows three concurrent forces, and these are this one. So, all these forces are meeting at a point, therefore, they are concurrent forces. Now, we discuss Newton's laws of mechanics. Newton provided three laws which form the foundation of mechanics. These are: first law states every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. This law is also called law of inertia. Then second law, the change of motion is proportional to the natural force impressed in a direction of the straight line in which the force is impressed. Here this force is external force acting on the body. Mathematically, this law is stated as F is equal to m times A. I put arrow here to make it F and A are vector, whereas mass is a scalar. F is the applied force, applied external force on the body, m is the mass and A is the acceleration. Now, they F and A, since they are vector, therefore they should be indicated in bold faced letters, or one should put arrow in the way I have put here. Now, third law is that for every action there is an equal and opposite reaction. Now, interesting point is that the first two laws of Newton are valid only in an inertial frame of reference. An inertial frame of reference has a constant velocity with respect to another inertial frame of reference, that is, it moves at a constant straight line. Now, the question is that which frame of reference is inertial? Inertial frame of reference is that frame of reference which moves with respect to another inertial frame of reference with a constant velocity. However, we must find out one inertial reference frame. For example, on the earth, when we design some machines in our lab, we find out that Newton's laws, first two laws, are valid in it. Force is applied on the body, then it accelerates, and acceleration is proportional to force, mass times force. So, therefore, here this law holds good. Therefore, we know the earth is inertial reference frame as far as our design of machine is concerned. Now, any frame of reference like a moving cart in a straight which is moving with a straight line, that can be considered inertial frame of reference. It is having constant velocity. So, therefore, this is inertial reference frame. However, that when we study planetary motion, then that cannot be considered, earth cannot be considered inertial reference frame. So, is there means it is almost it is impossible to find out any absolute inertial frame of reference. Therefore, it is just it is a concept with which that you can find out. So, for practical purpose, for designing the machine, we consider the earth as inertial reference frame, and we measure the other inertial or non-inertial frame of references with respect to this. Now, there Newton also provided a law of gravitational attraction. Two particles will be attracted towards each other along their connecting line with a force whose magnitude is directly proportional to the product of the masses and inversely proportional to the distance squared between the particles. So, F is equal to g times m1 into m2 divided by r square, where g is called the universal gravitational constant. By this, you find out the value of the force, and this force is given by g is equal to m1 m2 r square. Then, if you have got a particle which is freely falling under gravity, you can find out after applying the Newton's law, you can find out what is its acceleration. That will be called gravitational acceleration. Okay, that so like that there are some other. So gravitational force of the gravitational attraction is called a fundamental force. Now we discuss the parallelogram law, which was given by Stevinus in 1548 to 1620. He was the first to demonstrate that the forces could be combined by representing them by arrows to some suitable scale and then forming a parallelogram in which the diagonal represents the sum of the two forces. In fact, all vectors should combine in this manner. You have a force, two forces are there, then make the parallelogram. This is the thing, and then the force is in that direction. Now, now here, this is force OA, this is F2, OB is F1. Now this I am drawing from B, I am drawing a line parallel to OA and of the same length as OA, and from then joining A to this will be parallel to this one, that OB, then this is the diagonal, this is the resultant force R. Therefore, this is this one. Now, the like parallelogram law, there is a triangle law. If the two forces acting simultaneously on a body are represented by the sides of a triangle taken in order, then their resultant is represented by the closing side of the triangle in the opposite direction. Now, for example, here if we have see we understand parallelogram law. Here one force is this, another force is this. These are two sides of the parallelogram. Complete the parallelogram, make the diagonal, that is the resultant force. Now consider this triangle. This is OC, this is OA. So therefore this is F2. Then you have got AC. Then after that you have got OC. So therefore what happens, that if you consider that so in this triangle OAC, OA represents one force, AC represents another force, that is F1, and the resultant is of course given by R. This R is basically in the is represented by the third side. But if we move in a cyclic manner, then this is OA, OC, third side should be CO like this, but this force is of course in the opposite direction. So therefore it is written that if the two forces acting simultaneously on a body are represented by the sides of a triangle taken in order, then their resultant is represented by the closing side of the triangle in the opposite order. Like if one force is represented like this, other is represented like this, okay, then we close the triangle like this. However, we make the arrow in the opposite direction. So here it is like this. So now this is a triangle law. Now like we have Newton's law for which relates the force and acceleration or maybe linear change of linear momentum. We have Euler's law, which states the rate of change of angular momentum of a body about an origin O equals the moment impressed upon it about the origin. So rate of change of angular momentum, rate of change of linear momentum gives us force rate of change of angular momentum of a body about an origin O equals the moment impressed upon it about the origin. For the time being, we considered O to be a fixed point in the inertial frame of reference. Now, there is a principle of transmissibility which states that the state of rest or of motion of a rigid body is unaltered if a force acting on the body is replaced by another force of the same magnitude and direction, but acting anywhere on the body along the line of action of the upright forces. That means the force behaves like a sliding vector. In the following animation, in this, suppose this is the thing, two blocks are joined by a rigid rod. Now, here I am applying a force on block A, then both the blocks are moving, okay, because this is they are connected by rigid rod. Then I am applying the same force F, but now I am applying on B, by block B, it is being pulled here. Then also it is, the motion is same, it is unaffected by this thing. Whereas now okay, so in the, if the system is moving on a frictionless surface, then the acceleration of the system in both the cases is given acceleration is equal to applied force divided by total mass. We do not ask that where the applied force is acting, it is independent of the point of application. Now, let us see this, you have seen, let us go see the other things. If the blocks are connected by springs, this is the thing, then the system becomes non-rigid. In this case, if I apply a force F, then first the block A will start moving, and after the spring has stressed sufficiently, then the block B will also move. On the other hand, if we apply the force on this object like this, then first this block will move, then after that the another block. So, therefore, if the force is applied initially, the acceleration of B will be much more compared to A. If the force is applied on A, then initially the acceleration of A will be much compared to B. Thus, the point of application of force matters. To conclude, principle of transmissibility is valid only for rigid bodies. Now, we define the moment. The moment of a force about a point O is the cross product of R and F, where R is the position vector of a point on the line of action of force with respect to O. So, therefore, F is equal to R cross M is equal to R cross F. This is R cross F and this is like this. Now, this one here the force is acting and this is the line of action. On this line of action, I have taken a point here. This point has been taken, and now I take this as a, suppose this is my origin point. From here I join this point, then this becomes my position vector. I could have taken any other point also. In that case, the position vector will change. However, when we find out the cross product R cross F, then we should get the same vector. So, this is M is equal to R cross F and this is the thing, and the direction, if we represent F as a vector, R is a vector, then cross product is a vector, that will provide the direction of the moment. So, therefore, moment is a vector like the force. Just as force has a tendency to translate the body, moment has tendency to rotate the body about the point. if we apply a force on this body, it may rotate about this axis. It has a tendency to rotate the body about this axis, therefore it has got this thing. So moment has a tendency to rotate the body. Now we have to follow certain sign conventions. If the force has tendency to rotate the body in counterclockwise sense, then the moment is considered positive. If the force has tendency to rotate body in clockwise sense, moment is considered negative. A convenient way to find out the direction of the moment is as follows. Imagine to stand on the line of action of the force. If you just stand on the line of action of the force, look towards arrow, then if the point about which you are interested to find out the moment, if it falls towards your left hand side, then the moment will be considered positive, and if the point falls about the right hand side, then the moment will be considered negative. For example, if I take a point like force like this, there is a point O here. If I stand on this force and I look towards the arrow, this point O is towards the left hand side, therefore the moment is positive and it has a tendency to move the body about point O in the counterclockwise direction, whereas if the point O is this side, then the moment of F will be negative. So this is the thing. So we stand on the line of action of the force, look towards the arrow. If the point falls towards this one, okay, left hand side, then the moment is positive, otherwise it is negative. However, this is just the sign convention which is followed by most of the people. If you want to say a force which produces clockwise movement, clockwise rotation, that can also be considered positive. So it is just a matter of sign convention, but one should follow for solving a problem, one problem, he should follow the same convention. Now there is a theorem of Varignon. It states that moment of a force about any point is equal to the sum of the moments of the components of that force about the same point. So this theorem helps us to find out the moments easily. That in that case, that means if there is a force and I am interested to find out its moment about this point, I can resolve this force into two components and then I can find out the moment of these two components about this point O and add them, okay, then it will be equal to the moment of that force. This theorem can be easily proved. To prove this theorem, consider the force R acting in the plane of the body shown in this one, in this figure. Suppose we have got this point is there. Now in that a force R is acting. Now resolve the force into two components, that is Q and P, and you have to find out about point O here. Now we can see that the moment will be R cross R, but R can be written as P plus Q into R. So using the distributive law of R cross products, we have M0 is equal to R cross R, that is R cross P plus R cross Q. Now R cross P is the moment of force P about R, whereas R cross Q is the moment of force about Q. Therefore, it says that the moment of R about O equals the sum of the moments about O of its components P and Q. This has proved the theorem. Varignon's theorem need not be restricted to the case of two components, but it applies equally well to three or more components, where we but we have to be consistent in taking the sign of the moments. Now we have defined the moment about a point. Now, let us discuss moment about an arbitrary axis. We can obtain expression for the moment m lambda of f about any axis lambda through O. Now, this is the point O, and this is the force F. Therefore, take any point on the line of action of the force, join it by O. This provides you position vector R. Take the cross product R cross F, it will give you some vector. That vector is represented by M0, MO. MO is the moment of the force F about point O. Now, if you have got any arbitrary axis in the lambda direction and this unit vector is indicated by n, this vector, that means in this direction you take a vector whose magnitude is 1 and direction is this is, then we have to find out m lambda, that means moment of the force F about the axis lambda, that is the thing. So, if n is a unit vector in the lambda direction, then we can use the dot product expression for the component of a vector to obtain m0 dot n. We can have the dot product, we can take the dot product of these two vectors m0 n, which will be basically the projection of m0 on this line, because in dot product, suppose you have a vector here, another vector here, take the dot product. Therefore, this is just the projection of this vector on this vector. So, this is will be because this vector is a unit vector. So, this is like that m0 cos theta. Now, here that this is, if n is a unit vector for the component to obtain the component of m0 in the direction of lambda, this scalar is the magnitude of moment of f about lambda. Now, to obtain the vector expression for the moment m lambda of about A, multiply the magnitude by the directional unit vector n to obtain m lambda is equal to R class F. R class F is a vector, that is basically m0. Then you take the dot product with n, that is m0 dot n, and this is the magnitude and the direction is same as the direction of that lambda. So, therefore, we attach n here. This is a scalar quantity, R class F dot n is a scalar quantity and n is this one. So, this is a moment about that an arbitrary axis, this one. Now, we discussed about couple. The moment produced by two equal opposite and non-collinear forces is called a couple. We have two equal, this is was opposite, but they are non-collinear, they are not acting in the same line, therefore, they will produce couple. They will have tendency to rotate the body. Their net resultant is 0, because if we add them, we will get 0. We may express the moment of a couple by using vector algebra. Now, here this is that now supposing we make these are the two forces acting here, and then if you have got a point O, with that this point you join this point A, this point B. So, this will give you R A, this will give R B. So, M will be equal to R A class F plus R A class minus F, that is it will give R A minus R, this is, if we indicate it by R, this is RA class minus RR into F, where RA and RR are position vectors which run from point O to arbitrary points A and B on the line of action of this one. Now, in this case, this is B, in this case RA minus RB is equal to R. Therefore, we can express M as M is equal to R class F. Here the moment expression contains no reference to the moment center O, and therefore is the same for all moment centers. Thus, we may represent M by a free vector. So, M is a free vector, that means we can have this, suppose this is a couple, these are the two forces, okay. Their moment M is a free vector, it is not acting at any particular location. Even if we take any point O, about that we find out the moment, that is same. Another point we take this place, then also the moment is same. So, it is a free vector. Direction of M is normal to the plane of the couple, and the sense of M is established by the right hand rule, okay, right hand side rule, that when, okay, maybe anti-clockwise moment couple can be considered positive, because the couple vector M is always perpendicular to the plane of the forces which constitute the couple. In two-dimensional analysis, we can represent the sense of a couple vector as clockwise or counterclockwise by one of the conventions. Now, this is a counterclockwise couple, we have just made this type of convention, this is a clockwise type of this thing. We can also represent it like this, counterclockwise couple, like this, clockwise couple, this. It is a free vector, it can be shown at any location. That means, even here I can show like this. Now, here let us discuss the resultant of the forces acting on the body. Now, for the system of forces F1, F2, F3 acting on a body, like this is a body in which number of forces are acting, like here I have shown F1, F2, F3, and this is a point P. What can be done? That you can shift these forces from here to here, but you can also, then you have to apply some couple to balance it. So, therefore, we may move each of the force to the arbitrary point O, and if we can introduce a couple for each force transferred. Now, here suppose we move force F1 to that position O, then if we introduce a couple, that we also have to introduce a couple for that, because suppose this is a force P, this force acting here. Now, what I am doing, that this can be transferred at this point. How I apply two equal and opposite force at this point, okay. Then, if I consider that these two forces are constituting the couple, like this was F1 force acting here, this is another F1 force acting here, this is the force F1. So, this F1, this F1 is constituting a couple, and that can be moved in this direction. So, therefore, this is a couple. So, therefore, net effect is that there you have another force whose line of action now passes through O instead of this point say A. At the same time, there is a couple acting here, because that these and these forces. So, in this way we can transfer all the forces to this one. So, point O. Then we have a system of concurrent forces at O and a system of couple vectors. The concurrent forces may then be added vectorially to produce a resultant force R, and the couple may also be added to produce a resultant couple M. Okay. Now, therefore, now this couple has been taken with respect to point O. So, therefore, now you have that this is R and this can be called a moment. So, this is like that. Now, the point O selected as the point of concurrency for the force is arbitrary, and the magnitude and the direction of M depends on the particular point O selected. The magnitude and direction of R, however, are the same no matter which point is selected. So, therefore, if you know, like giving a simple example, if you have a force F, 5 Newton force acting at a distance of 1 meter from O, that can be replaced by a force by this one O. Force is now acting at O itself, but there is a corresponding couple also or moment, that is 5 Newton meter. Okay. I could also have transferred this 5 Newton here at the middle. So, therefore, what happens, I could have shown it like 5 Newton and this distance was 2.5. So, therefore, it is this is 0.5. So, this is 2.5 Newton meter. The magnitude and direction of, so you see that in this case, in these two cases, the magnitude of the and direction of force remains same. 5 Newton is same as 5 Newton, although we transfer the force. However, that this magnitude of the moment has changed, the magnitude and they similarly the direction can also change. In this case, the direction has not changed. In general, any system of forces may be replaced by its resultant force R and the resultant couple M. In dynamics, we usually select the mass center as the reference point. We try to find out the resultant forces acting at the center of mass, and we find out the moment also about that point. The change in the linear motion of the body is determined by the resultant force, and the change in the angular motion of the body is determined by the resultant couple or moment. In statics, the body is in complete equilibrium when the resultant force R is 0 and the resultant couple M is also 0. If there is a resultant couple acting, then the body will have tendency to rotate. Thus, the determination of resultants is essential in both statics and dynamics. Now, we discuss about wrench resultant. When the resultant R is in the same direction as the resultant moment M, then this is called a wrench resultant. In this case, this is the thing. It is a positive wrench, that means direction of R and direction of M is same. Negative wrench means direction of R and direction of M are opposite. So, when the resultant couple vector M is parallel to the resultant force R as shown in figure this one, the resultant is called a wrench. By definition, a wrench is positive if the couple and force vectors point in the same direction and negative if they point in opposite directions. A common example of a positive wrench is found with the application of a screwdriver. When we move a screwdriver, it applies a moment which is along the axis of the screw, and there is a thrust force which is also in the direction of a screw. Any general force system may be represented by a wrench applied along a unique line of action. So, this is the point. Then we discuss the resolution of forces. The resolution, it is the resolution is the inverse of addition. Like two forces can be added to make the resultant. Similarly, a force can be resolved in two components or several components such that the addition of these forces provide the same force. So, whereas the resultant of the force is a unique vector, resolution of force may give many solutions. Okay. However, if we fix up the directions, then you may get unique. Say for example, now this is a force F. Now it can be written as the sum of this as well as this force. So the force has been resolved into two components, O, A, B. Right. So therefore, the most common two-dimensional resolution of a force vector is into rectangular components. Let I and j be the unit vectors in the direction of x and y. This is I, so j, this is jth component. So the force F has been resolved into two components. This is Fx and this will be Fy, and the resultant force is shown by force F here. So therefore, this has been resolved. So we can write F is equal to Fxi plus Fyj, where F is the force, Fx is the component of the force. This will be indicated by bold faced, but Fx is just a component in the direction of I, unit vector I, then Fy and j. It can be easily shown that the sum of the resolved components of several forces is equal to the resolved component of the forces. Okay, so that means if you have one force and another force is acting, okay, this is F1, this is F2. If you combine these two forces, you get the resultant force. If you take the resolved component along a particular direction, let us say x, that is same as if you take the resolved component of F1 and then take the resolved component of F2 and then join. So therefore, this can be done. So this concludes the basic concepts about the this one, engineering mechanics. So we have, in this lecture, we have discussed the basically the definition of engineering mechanics. We have discussed about the continuum hypothesis, which will be applied while studying the rigid body. Rigid body is basically a hypothetical concept. When we apply the force, if the distance between two particles does not change significantly, then the body can be considered as a rigid body. Actually, always there is some change between the two particles when you apply a force, but it can be considered. Then we discussed the Newton's laws. Newton's first law and second law are valid only in inertial reference frame. Then we discussed about the gravitational force acting between the two particles. We also have told that the forces can be resolved, and the resolution of the forces offers many advantages because the resultant can be easily found. We can suppose there are two vectors, you cannot construct graphically again and again that parallelogram, and although there is a formula by which you can find out resultant, that formula is R square, magnitude is P square plus Q square. This force is P, this is Q, P square plus Q square plus 2pq, and if this angle is alpha, this is cos alpha. And similarly, you can find out the direction also. However, if one can resolve the forces in the components form and express the force as a vector quantity, let us say one force is like this, F1 is equal to 3I plus 4J plus 5K. Another force is F2 is equal to minus 7I minus 2K. Then these two forces can be joined and this becomes F1 plus F2 is equal to minus 4I plus 4J plus 3K. So then you can find out the magnitude of the forces. Now similarly, if you have express the force in this form of the components I, j, k are the unit vectors along say 3 orthogonal direction, that is x direction, y direction and z direction. Now two forces, then you can find out the moments also. R cross F is the moment. Now this can also easily be found out. You know how to find out the cross product. If that is, we can have R cross F is equal to basically I j k in the form of a determinant. We can write this is Rx component, this is Ry, Rz and this is Fx, Fy, Fz. Now then we have this just introduced that about the Euler's law, which is related to the angular momentum, and for complete then we have told the concept of the couple and this thing. For complete equilibrium of the body, the resultant force must also be 0 and the couple acting on the body should be 0. These are the necessary and sufficient condition for a body to be in equilibrium. Okay. Now yes, this is so just this one. Now you can in the next lecture we will elaborate on these conditions in detail. This is now here I will just recapitulate one formula which is already taught at the +2 level, that is this one here. This is R is equal to under root p square plus q square plus 2pq cos alpha, and then this makes angle theta from here. Therefore tan theta, this angle is alpha, alpha is this angle theta, tan alpha tan theta is equal to q sin alpha divided by p plus q cos alpha. That is the thing. So this is theta is the direction. So this is about this thing. So yeah, that we will be discussing in the next lecture.